Have you ever watched the needle of a compass twitch when it's near a wire carrying current? That invisible twitch is the power of magnetic force in action. Hello students, today we step into the fascinating world of moving charges and their interaction with magnetic fields. Magnetic force is not like gravitational or electric force that pulls directly. Instead, it acts in a perpendicular direction only when the charge is in motion. It's nature's clever twist, literally. The direction of this force isn't arbitrary, it follows a rule. For positive charges, we use the right-hand rule. Point your fingers in the direction of velocity, your palm towards the magnetic field, and your thumb points to the force. This isn't just theory. It's the principle behind electric motors, particle detectors, and even how Earth's magnetic field steers charged cosmic rays. Let's now put this force into a precise mathematical form. The magnetic force on a moving charged particle is given by the Lorentz force equation F equals Q times open bracket V cross B close bracket. Here, F is the force vector, Q is the charge, V is the velocity of the charge, and B is the magnetic field. Since it's a vector cross product, the direction of the force is perpendicular to both velocity and magnetic field. Using the right-hand rule helps visualize this. Now, if the velocity is parallel to the field, no force acts. Why? Because the sine of 0 degrees is 0. The magnitude of the force is given by F equals QVB sine theta, where theta is the angle between velocity and a magnetic field. In practical applications, like in a cathode ray oscilloscope, this force is used to deflect the electron beam precisely. Let's now shift gears from a single charge to a stream of charges, that is, electric current. When a current-carrying conductor is placed in a magnetic field, it too experiences a force. This is because the moving electrons inside the wire feel the magnetic force. The equation becomes F equals I times open bracket L cross B close bracket, where I is the current, L is the length vector of the wire, and B is the magnetic field. Again, the right-hand rule comes to the rescue. Fingers point along current, palm in the field direction, and the thumb gives the force. This force is the key behind the working of electric motors, where rotating coils in magnetic fields generate mechanical motion. The force becomes maximum when the wire is perpendicular to the field and vanishes when it's parallel. Now, let's examine how magnetic force bends paths. If a charged particle enters a uniform magnetic field at 90 degrees, it starts moving in a circle. Why? Because the magnetic force acts as a centripetal force. Let's derive this. Magnetic force F equals QVB and centripetal force is mv squared by r. Equating the two gives r equals mv by qb, the radius of the circular path. The heavier the particle, or the faster it moves, the larger the circle. The time to complete one revolution is t equals to pi m by qb, and what's fascinating, it doesn't depend on the speed or radius. This principle powers cyclotrons and mass spectrometers, which separate particles based on their charge-to-mass ratio. Imagine all of this with just a field and a force. So far, we've discussed how magnetic force affects direction, but what about energy? Here's the twist: magnetic force does no work. Since it always acts perpendicular to motion, it doesn't change the speed or kinetic energy, only the direction. Think of a charged particle circling in a magnetic field. It spins forever, same speed, no energy gained or lost. That's why magnets can steer particles but can't speed them up or slow them down. This is different from electric fields, which do perform work. The magnetic field is like a cosmic traffic cop. It redirects but doesn't accelerate. Alright, time for some serious application. Imagine a proton with kinetic energy of 3.2 times 10 to the power negative 19 joules entering a uniform magnetic field of 0.02 Tesla at 90 degrees. How do we find the radius and time period of its circular path? Step 1. Convert kinetic energy into velocity using V equals square root of open bracket to K divided by M close bracket. Substituting values, we calculate V. Step 2. Use the formula for radius, R equals mv divided by qb. Plug in values, mass of the proton, velocity from step 1, its charge, and the magnetic field. Step 3. Calculate time period using t equals to pi m divided by qb. Notice that t doesn't depend on velocity, a unique magnetic feature. These calculations show how we trace particle paths in accelerators and magnetic fields, essential in both research labs and medical imaging. Let's quickly revise what we've learned about magnetic force. Magnetic force acts only on moving charges and is perpendicular to both velocity and magnetic field calculated by F equals qv cross b. It does no work but alters the direction of motion, causing circular paths in fields. In wires, it creates motion, powering electric motors. In particle physics, it separates and steers charged particles. From deflecting electrons in TVS to guiding ions in mass spectrometers, magnetic force is a silent architect in countless devices around us. I hope now you appreciate how this invisible vector force shapes the very motion of charged particles, from your classroom experiments to advanced particle accelerators. See you in the next topic, where we'll continue to explore how electricity and magnetism dance together in this beautiful physics symphony.